Good evening, everyone. Today in this lecture, we'll be discussing about the potential and potential due to point charge. In the last lecture, we finished about the electric fields, right? But in this lecture, we'll be discussing about the potential and potential due to point charge. Let's suppose that this is the charge plus Q, right? And we have some test positive charge at infinity, right? And this is the charge plus Q, and at infinity, we have test positive charge, right? Let's suppose this is the test positive charge, right? And let me call this as Q, right? This is the Q charge here at infinity. Now at infinity, if we want to bring this charge in the field of this plus Q charge, right? We want to bring this charge. We know that because of this plus Q charge, there is an electrostatic field spread throughout the space, right? And suppose that we want to bring this charge at some distance r in the field of this plus Q charge, right? So we want to bring this charge Q from infinity to this point R in the field of this plus Q charge, right? And we know that there will be electrostatic force of repulsion between this Q charge and this plus Q charge, right? Electrostatic force of repulsion will be there, right? So it means that if there will be electrostatic force of repulsion between this Q charge and plus Q, then this electrostatic force of repulsion is going to be in this direction, right? It's going to be in this direction. To bring this charge to the point Q to the point P at a distance of r from this plus Q charge, we need to do external work, right? Then only we can bring this charge from infinity to the point P at a distance of r from this plus Q charge, right? So one more important point is that all the measurements, all the distance here are measured from the infinity, or we can say that the reference point here is infinity, right? So F is the electrostatic force, and let's suppose that we're displacing this charge by a displacement of dx. This charge Q has been displaced by a displacement of dx. Then the work done will be given by, that will be F dot dx, right? F dot dx, where dx is nothing, it's a small displacement, right? And we have to do work against this repulsive force, right? And one more important point is that we're bringing this charge, test charge, slowly and steadily from infinity to the point P at a distance of r from this plus Q charge, right? From this plus Q charge at a distance of r, right? So it means that at any instant, the change in kinetic energy of this charge Q will be equal to 0. Or we can say delta K, that's the change in kinetic energy at any instant for this test charge when we bring it from infinity to the point Q in front of this plus Q charge or in the field of this plus Q charge. So the change in kinetic energy has to be equal to 0, right? Or we can say that we're bringing this charge slowly and steadily from infinity to the point Q, right? We can see that the direction of this displacement, the direction of this displacement vector is opposite to this electric field, right? The direction of this displacement vector is opposite to this force, and this is the direction of this displacement, and this is the direction of the force, right? And we have to do the work against this force, right? So it means that angle between force and displacement vector is going to be equal to 180 degree, right? And F dot dx we can rewrite it as, let's suppose dw is the small work done in displacing this Q charge by displacement of dx, right? So we can write it as F dx cos of 180 degree. It's a dot product of the force and displacement, right? And cos of 180 is nothing, it's equal to -1, right? So we'll be left with F dx, right? Or we can write this small work dw as minus F dx, correct? And the force we have to apply to bring this charge, if we have to bring this slowly and steadily to this point P, we have to at least apply the same amount of external force as there is the repulsion due to this plus Q charge. So this force has to be equal to at some distance x, that will be equal to kq q upon x square, right? This is the electrostatic force, correct? So the work done GW will be equal to minus kq q upon x square, right, into dx. And we know this charge q is nothing, it's a unit test charge, right? That's equal to 1 unit. It means that work done will be nothing, that will be GW, that's equal to minus k q upon x square dx, right? And if we integrate this from infinity to the r, we will calculate the work done, total work done in bringing this charge q to the point P. So we'll integrate it to calculate the total work done. So integrating it on both sides, we'll be left with kq upon x square into dx with the limits infinity to r, right? So k and q is a constant, it will come out of the integral. We have to integrate dx upon x square with the limits infinity to r, correct? So the integration of 1 upon x square with respect to x is nothing, it's equal to minus 1 upon x, right? Minus 1 upon x with the limits infinity to r, right? So our integral of dw will give us the total work done, that will be equal to kq upper limit minus lower limit, that's 1 upon r minus 1 upon infinity, right? And we know that 1 upon infinity is nothing, it's equal to 0, right? So from here we can see that work done in bringing this charge q from infinity to that point in the field of this plus q charge is equal to kq upon r, right? So this is what we call as the potential V, right? This is nothing, this is what we call as the potential due to point charge. Potential due to point charge. In general, we define potential as is the work done in bringing a charge, unit charge, in the field of some external charge to that point from infinity, right? So if we have any charge distribution present, and if we want to see what is the potential due to this charge distribution, then what we would do is that we'll bring a unit positive stress charge from infinity to some point in the field of the given charge, and the work done in bringing that charge from infinity to that point in the field will be called as the potential, right? So this will be the potential due to point charge here, right? This will be called as potential due to point charge, correct? So work done is equal to kq upon r. It means that suppose plus q charge is there, and if we want to see what is the potential at some distance r, right? Let's call this potential V at this point P. Then this potential Vp will be nothing, that will be equal to kq upon r, right? So it will be equal to kq upon r, correct? And suppose if the charge is negative, let's suppose minus q charge is there, then the potential at P at some distance r will be a negative potential, right? In this case, we can define this Vp as minus kq upon r, right? So this will be a negative potential at this point, right? So the potential can be positive, it can be negative, right? And it can be even zero, right? So important point here is potential V can be positive, negative, or zero as well, right? Or zero as well. Here in this case, we selected the reference point as infinity. It means that we are bringing the charge from infinity to the point in the field of some external charge, right? And we calculated the potential due to that charge plus q, right? But one more point is that if the reference is changed, then the potential may change, right? So important conclusion here is that potential due to some charge, it depends upon the reference, right? So V is reference dependent, right? Reference dependent. And for point charge distribution, for point charge, we by default take the reference as infinity because we know that at infinity the electrostatic field dies out. Or we can say that electric field intensity due to point charge at infinity is equal to 0. And by default, we take the reference for point charge as infinity. You can take any other reference as well, right? So V is reference dependent, correct? So it means that suppose that for somebody, if somebody is calculating the potential at some point as let's suppose 10 volt, and another person is calculating the potential at the same point as plus 5 volt, we cannot say that whether first person is correct or the second person is correct. We can say that the both persons are correct because the reference for the first person may be one and the reference for the second person may be the different reference. If they are measuring the potential with respect to the same reference, then they must measure the same potential. Otherwise, if the reference points for both the persons is different, then the potential they will measure will be different, right? So the SI unit of this potential, SI unit of potential potential is, we define it as work done per unit charge, right? Per unit charge. So work done here was KQ upon R for the test charge Q. So work done potential is defined as work done per unit charge, correct? And the SI unit of work is joule and the SI unit of the charge is coulomb. We define the SI unit of potential as joule per coulomb, or we call it as volt, denoted by this symbol V, right? So the SI unit of potential is joule per coulomb, or we also called it as volt, right? Denoted by V, correct? So let's discuss about the conservative fields associated with the electrostatic charge. There is one more important point, that whenever we displace a charge, right? Whenever we displace a charge, let's suppose we have this charge plus Q here. We have this charge plus Q here, and this is charge Q here, right? This is charge Q here. This is charge Q. And let's suppose we try to displace this charge Q from its position and bring it here, right? We bring this charge Q here at this was point P. Let's call this point as Q, and this is the final position of this charge, right? This the Q position is the final position of this Q charge, right? Now it means that if we displace this charge, from its initial position to some final position, right? Let me call this as R initial position. From here to here, this is called as Ri, and from here to here, we can call it as final position, right? And we need to do some work, right? We need to do some work. And whenever we do the work in this field, then this work done in case of conservative fields, in case of conservative electrostatic fields. By conservative electrostatic field, we mean that generally the field due to the static charge is a conservative field, right? Then this work done in the conservative fields is stored as energy, what we call as potential energy, right? The work done in conservative fields, work done in conservative fields stored as work done in conservative fields is stored as potential energy, right? That's the one of the important aspects of the conservative fields, be it gravitational potential energy, right? Be it spring potential energy, be it electrostatic potential energy, right? These energies are only possible when the fields are conservative in nature, right? By conservative fields, we mean that if the work done in that field is independent of the path, right? Is independent of the path, correct? Means that let's suppose this is the charge plus Q here, right? And this is the charge Q here. Let's suppose I displace this charge Q to this point like this, or I can displace this charge Q like this from point P, from point P, from point P to point R, right? And I can also displace this charge q like this, or we can also displace it like this. So we have different paths to bring this charge from point P to point R, right? So all these paths are different, right? So let's suppose W1 is the work done in this path, and W2 is the work done in this path, W3 is the work done in this path, and W4 is the work done in this path. And in case of conservative fields, if the field is conservative, then this work done will be independent of the paths followed, right? It means that for all the paths, in case of conservative fields, the work done will be same. Provided if the initial and final points are same, then the work done will not depend upon the path, right? Work done will not depend on the path. The work done through all the paths will be equal, right? Or we can say work done is path independent, right? Work done is path independent. So in case of conservative fields, work done is path independent, correct? Then on what factors does this work done depend? It depends only on initial position and final position. Initial position and final position, right? And final position. Initial position and final position, right? And one more important point is that work done only depends upon the initial position and final position. It will not depend upon the path followed by displacing this charge from point P to point R, right? Since initial and final position is same, initial is P for all the paths and final point is also R for all the 4 paths. So the work done W1, W2, W3 and W4 will be equal, right? And one more point is that if initial and final position is same, if initial and final position is same, right? Is same, then work done is equal to 0. Then work done is equal to 0, right? Then work done is equal to 0. It means that in case of conservative fields, the work done in a closed path is always equal to 0, right? It means that let's suppose that here we have this charge. Let's suppose that this is the plus q charge, right? And this is the q here. What we are doing is that we just displace this charge like this and finally bring this charge to the same position, right? We displace this charge like this, right? In a closed path, right? And bring this charge at the same initial position. Then the work done by this external force will be equal to 0. So we can say the work done in this case will be equal to 0, right? So work done in a closed path in case of conservative fields is equal to 0. And one more point is the work done in conservative fields, if it is non-zero, it's stored as the potential energy of the system, right? It's stored as the potential energy of the system, right? And work done is independent of path followed by the charge from one position to another position. For two different paths, if the initial and final position is same, then the work done has to be same, right? So all these fields we call as conservative fields. And similarly, electrostatic field is one of the conservative fields with us. So it means that whenever we displace a charge in presence of a conservative field or the electrostatic field, then the work done will be stored as the potential energy of the system, right? That work done will be stored as the potential energy of the system. So it means that we have to calculate potential energy. What will be the potential energy due to 2-point charges, right? Due to 2-point charges. It means that, let's suppose that this was the plus q charge. And once again, what we did is that there was some charge q, and this charge q was initially at infinity, right? This was initially at infinity. I call this as initial position r, right? That's equal to infinity. And finally, we bring this charge at a distance of r, in the presence of this electrostatic field in front of this plus q charge at a distance of r, right? Now we have to calculate the work has been done, right? We have to do some work to bring this charge from infinity to point P, right? And we have to do some work, right? We have to do some work, and we calculated that work done in the previous slide. You can see that the work done that was calculated as here. The work done was calculated here as it was q upon x square, right? q upon x square. It means that suppose if it displaces this charge by dx distance, then the work done will be dw. It will be equal to minus q upon x square into dx, right? Now to calculate the total work done, we will integrate it from initial limit to the final limit, right? On the both sides. So this will be the total work done, right? So minus kq upon, so we'll integrate this dx and x square. It will be minus 1 upon x with the limits infinity to r, right? So it means that that's q upon with the upper limit and the lower limit as 1 upon r minus 1 upon infinity, right? That will be equal to 1 upon infinity will be equal to 0. That will be equal to k capital Q small q upon r, right? And this work done, we said that is stored as the potential energy U. So potential energy stored within this system is nothing. It's equal to q upon r. So for these 2 point charges, this is the potential energy, right? Stored between the system of 2 charges, right? This is the potential energy, correct? So this is the potential energy stored between the system of 2 charges, right? Let's suppose that if we have 2 positive charges, plus q1 here and plus q2 here, right? And they're separated by distance r, right? Then the potential energy of the system will be equal to, that will be k q1 q2 upon r, right? Suppose we can have 2 negative charges, minus q and minus q2 here. Then the potential energy for this system will be minus k q1 . So the potential energy due to 2 point charge was calculated as potential energy due to 2 charge was calculated as, that was U equal to k q1 q2 upon r, right? K q1 q2 upon r, correct? So this was the potential energy due to 2 point charges which are separated by a distance of r, right? These 2 charges are separated here with a distance of r, right? And if 2 negative charges are there, minus q1 and minus q2 here, the potential energy of this system will be equal to, once again, plus k q1 q2 upon r, right? And let's suppose that one charge is negative, another charge is positive, right? Once again separated by the distance of r. Then the potential energy of the system will be minus k q1 q2 upon r. So it means that once again the potential energy can be 0, it can be positive, it can be negative as well, right? So that's how the potential energy of the 2 charges is calculated, and that's how the potential energy of the 2 charges depends. So we can clearly see that the potential energy here depends upon the distance between the 2 charges, right? And the product of the 2 charges, right? So the SI unit of any energy, SI unit of potential energy, we know that is joules, right? For any energy, the SI unit is joules. right? So for the same here, right? Potential energy of this SI unit of this potential energy will also be equal to joules, right? Let's move on to this slide here. So let's talk about this question. Let's try to solve this question. This is the question number 1 with respect to the potential energy calculation. The question says that find potential energy of the system shown. Also find work done in decreasing distance by 1 meter, right? It means that 3 coulomb and 2 coulomb charges are separated by distance of 4 meters here. And if we calculate the initial potential energy of the system, right? Initial potential energy of the system, that will be equal to K into 3 into 2 upon distance. That's 4 meter, right? So it will be 6 upon 4 into K. That will be equal to 6 upon 4. The value of K is nothing. That's equal to 9 into 10 to the power 9, right? 9 into 10 to the power 9. So it will be 54 upon 4 into 10 to the power 9, right? So we can write it as 13.5, right? So it will be 13.5 into 10 to the power 9 joules, right? So this will be initial potential energy of these two charges. Now we have to also find work done in decreasing the distance by 1 meter. If we decrease the distance between them by 1 meter, it means that we have to bring them close. We have to bring them close. Then the work done will be, I'm bringing this 2 coulomb charge at a distance of now 3 meters, right? It means that the potential energy is going to change. So the final potential energy here will be K Q1 into Q2, that's 3 into 2 upon distance square, upon distance, that's 3 meters. So this 3 and this 3 will get cancelled. We'll be left with 2K, right? We'll be left with 2K. That's the final potential energy, or we can write it as 2 into 9 into 10 to the power 9, or that's 18 into 10 to the power 9 joules, right? Now the energy has been changed from U initial to U final. It means that work has been done. Then the work done will be nothing. That will be equal to the change in potential energy. That's final potential energy minus initial potential energy. So it has to be equal to 18 into 10 to the power 9 minus 13.5 into 10 to the power 9, right? So it will be equal to 3.5 into 10 to the power 9 joules, right? So this will be the work done in displacing this charge. This will be the work done in displacing this charge from 4 meter to 3 meter, right? Let's discuss the question number 2 with respect to this potential energy, right? For the given charge system, find potential energy of system, and then we have to calculate work done in carrying a charge to infinity. It means that suppose we have done some work in assembling this charge 4 coulomb and minus 3 microcoulomb, right? Then this work done is stored as the potential energy in the system of this 4 microcoulomb and minus 3 microcoulomb. Then this potential energy will be nothing. That will be equal to K into 4 micro, that's 10 to the power minus 6 into minus 3, right? So we'll take minus sign here, into 10 to the power minus 6, and they are separated by a distance of 18 centimeters. So we can write it as 18 in terms of meters, that's 10 to the power minus 2 meter, right? So we can replace the value of this K, that's 9 into 10 to the power 9, right? In SI units, that's 4 into 10 to the power minus 12 into 3 upon 18 into 10 to the power minus 2, right? So this will be 9192, right? And this 2 and this will get cancelled. We'll be left with 2 here. So it means initial potential energy will be here equal to 3 into 2 will be 6. 6 into 10 to the power 9 minus 12 upon 10 to the power minus 2, right? So we'll be left with 6 into 10 to the power 9 minus 12 plus 2, right? So that's equal to minus 12. That will be equal to 6 into 10 to the power minus 1, right? And we have a negative sign here, so we have to use a negative sign here, so it will be a negative sign. So it means that's equal to minus 0.6 joules, right? So the initial potential energy of this system is nothing, it's equal to minus 0.6 joules, right? It's equal to minus 0.6 joules. It means that the potential energy of the system is minus 0.6 joules. Then if we have to carry a charge minus 3 coulomb to infinity again, then at least we have to do this much of work to bring this charge from this point here to the point at infinity, right? To the point at infinity. But the work done now will be positive, right? Now the work done will be positive. It means that work done has to be equal to change in potential energy, that's U final minus U initial, right? And we know that at infinity, the potential energy by reference is equal to 0, right? That means at infinity, the final potential energy will be equal to 0. We can say that at infinity, the final potential energy will be equal to 0. So it means the work done will be equal to final potential energy, that's 0, minus initial potential energy, that's minus 0.6. So that's equal to 0.6 joules, right? Plus 0.6 joules. So we have to do a positive work in bringing this charge from this position to infinity, right? So work done in carrying a charge to infinity is plus 0.6 joules, and the potential energy of the system is minus 0.6 joules, right? So let's discuss about one more point. One of the important points here. That's the potential. Due to the system of charge, right? We have to discuss about the potential energy due to the system of charge, right? So it means that suppose if we have n number of charge, right? If we have n number of charge, then how do we calculate the work done due to system of charge, or how do we calculate the potential energy due to the system of charge, right? It means that let's suppose that we can say it also has potential energy due to system of charge, right? Potential energy due to system of charge. Due to system of charge, right? So we have to calculate potential energy due to system of charge. It means that let's suppose we have charge Q1 here, and we have charge Q2 here, and we have charge Q3 here, and we have charge Q4 here, right? Let's suppose the distance between Q1 and Q2 is R1, 2, and distance between Q2 and Q3 is R2, 3, and distance between Q3 and Q4 is R3, 4, and distance between Q1 and Q4 is R1, 4, right? That's equal to R1, 4, correct? And let's suppose that distance between Q1 and Q3 is now Q1 and Q3 is now R1, 3, right? And we can say also the distance between Q2 and Q4, it's nothing, that's equal to R2, 4, right? So it means that the potential energy of the system will be the potential energy due to Q1, Q2, and potential energy due to Q2, Q3, potential energy due to Q3, Q4, and the potential energy due to Q4 and Q1, and the potential energy due to Q1, Q3, and the potential energy due to Q2 and Q4. It means that the total potential energy of this system, will be potential energy between 1 and 2, and potential energy between 2 and 3, potential energy between 3 and 4, and potential energy between 4 and 1, and also the potential energy between 1 and 3, and finally the potential energy between 2 and 4, right? So it means that we will have 6 terms here. We have 4 charts here, but the 6 terms of potential energy will be there, and we'll be adding all the terms of this potential energy, all the terms of this potential energies to get the total potential energy of the system, right? And this, it means that this much of work done is required to assemble the system, right? It means that this much of work is required to assemble the system to create the system of charges, right? And the system of these point charges. So potential energy, total potential energy, if we have to calculate for a system of charge, we have to look at all the combinations of the charges that are there, and finally add each and every potential energy to two charges, right? And then we can get the total potential energy of the system. It means that, let's suppose, if we have n charges, if we have n number of charges, if we have n number of charges, then total number of potential terms, then total number of terms is equal to n into n minus 1 upon 2, right? N into n minus 1 upon 2. It means that, let's suppose we have 4 charges here, right? Then the total number of potential energy terms will be 4 into 4 minus 1, right, upon 2. That's equal to 4 into 3 upon 2, and 2 and 2 will get cancelled. We'll be left with 6. So it means that we will have, for 4 charges, we will have 6 energy terms, right? We have 6 potential energy terms for 4 charges, and similarly for 3 charges, for n equal to 3, if 3 charges are there, we will have 3 into 3 minus 1 upon 2, right? That's equal to 3 terms only, right? So for 3 charts, we will have 3 terms only, correct? So let's try to apply this on some questions. Let's suppose we have this equilateral triangle here, right? We have this equilateral triangle here. And the side of this equilateral triangle is A, and we're placing Q here, Q here, and Q here, right? Now we have to calculate potential energy of system. We have to calculate the potential energy of this system. And to calculate the potential energy of this system, we'll look at all the combinations. The first combination will be between this Q and this Q, right? And then there will be combination between this Q and this Q, and finally we have the combination between this Q and this Q. It means we'll have 3 terms here, right? So the first term, U1 will be equal to KQ square upon A plus, and the second term, that's U2, will be equal to also KQ square upon A, and the third term we'll have once again KQ square upon A. It means the total potential energy U will be equal to 3 KQ square upon A. So the total energy of this system, total potential energy of this system will be 3 KQ square upon A, right? And similarly, if we have 4 charges placed on the square, corners of a square, right? If we have 4 charges placed on the corners of a square like this, suppose this is Q here, this is Q here, and this is Q here, and this is once again Q here. And the side of this square is A, right? Now in this case, we know that the total number of terms will be n into n minus 1 upon 2, right? So these will be 6 terms, right? It will be 6 terms. It means that it will be potential energy between this term and this term, right? And the potential energy between these two, and the potential energy between these two, and also the potential energy between these two, and the potential energy between the 2 charges at 2 corners, right? Diagonally opposite, right? So we'll have 6 terms like this. It means that if this is A, then this diagonal will be root 2A, right? This will be equal to root 2A. Then the potential energy, 4 terms will be because of 2 side charges, right? So we can write it 4KQ square upon A, and the 2 terms will be because of the 2 diagonally opposite charges. So it will be 2 times KQ square upon the distance, that's root 2A. So it means the total potential energy of the system will be equal to 4KQ square upon A plus 2KQ square upon root 2A. So this will be the total potential energy of the system, right? So that's how we calculate the potential energy due to n charge, or how we calculate the work done required to bring the system, or to create a system of n point charge in a space, right? So that's it for today. In the next lecture, we'll be continuing with the potential and potential energy further. We'll be discussing about the potential and the potential energy calculation for the continuous charge distribution, right? Till then, take care and goodbye.